Hello, now we're going to work through the problems assigned out of section 4.6. Before we start, I just want to remark what's 4.6 about? Factoring polynomials, finding roots of polynomials. Okay, we know if we can find roots of polynomials, if, for example, f of r is 0, then x minus r is a factor. So finding roots of polynomials corresponds to factors of polynomials. Why are we so interested in factoring polynomials? Well, we saw in the previous section that rational and polynomial inequalities are pretty straightforward to solve, provided that they are already factored. So if you have a polynomial or rational inequality that isn't already factored, you need to factor it first, which means you need to find the roots of the various polynomials involved, which is what this section is about, finding roots of polynomials. Okay, so let's get into it. So here we are asked, use the rational zeros theorem to list potential rational zeros of this polynomial, but don't actually check to see if they are zeros or not. So let's just go over what the rational zeros theorem says. Okay. So first of all, is the function a polynomial? If it's not a polynomial, then the rational roots theorem or the rational zeros theorem just doesn't apply at all. Yes, this is a polynomial. Is every coefficient an integer? So my coefficients in this case are 1, that's multiplying x to the 7th, and 1 is an integer. Negative 14 is multiplying x to the 4th, and negative 14 is an integer. 6 is multiplying x, and that's an integer. And negative 19 is the constant term, and that's an integer. So yes, every coefficient is an integer. If you don't have a polynomial, or if you have a polynomial where one or more of the coefficients aren't integers, then you cannot use the rational zeros theorem or the rational roots theorem. Okay. So here's what the theorem says, assuming both of these conditions are met. If p over q is a root of f of x, or a 0 of f of x, in other words, f of p over q equals 0, then p, the numerator, must be a factor of the constant term, and q must be a factor of the leading coefficient. Okay, so the question becomes, what does constant term and leading coefficient mean? Okay, so constant term means the number not multiplying any x's. The leading coefficient is the number multiplying the highest power of x. So in this particular case, my constant term is negative 19, and my leading coefficient is 1. Okay, so in this case, p is a factor of 19, or negative 19, but factoring is actually not, it does not care whether you have a positive or negative number, and q must be a factor of 1. So the factors of 19 are 1, 19, but don't forget negative numbers as well. These are also factors. Factoring does not distinguish between plus and minus. Okay, and factors of 1 are 1 and minus 1. So I'm going to erase up at the top. What are all possible fractions I can make where the numerator p is drawn from the list 1, 19, negative 1, negative 19, and the denominator q is drawn from the list 1, minus 1. So I like to be very methodical about this. I could have 1 over 1 or 1 over minus 1, 19 over 1 or 19 over minus 1, negative 1 over 1 or negative 1 over negative 1, negative 19 over 1 or negative 19 over minus 1. But you will notice there's some duplication here. Okay, so I have 1, negative 1, 19, negative 19, negative 1, 1, negative 19, and 19. Okay, because each of the numerator terms was allowed to be positive or negative, and each of the denominator terms was allowed to be positive or negative, we ended up with some duplication, okay, of choosing, for example, both positive or both negative would give me the same thing, and choosing numerator positive, denominator negative would give me the same result as a numerator negative, denominator positive. So these are all duplicates. Here is our actual list. Now what I do want to point out, okay, these are not all zeros of the function. Okay, you can just plug these things in and see that you cannot plug all of these in and get out a 0 at the end. The rational roots theorem does not say everything in this list is a root of the function. It only says that if you have a fraction that is a root of the function, it must be in this list. Okay, moving on. Same problem, use the rational zeros theorem to list the potential rational zeros. This is a polynomial. It's a polynomial of degree 7. The coefficients are -9, -1, +1, and 3. Those are all integers, so the rational roots theorem applies. So any rational root of the form p over q, p must be a factor of the constant term, which is 3, and q must be a factor of the leading coefficient, which is -9. So I can have ±1 and ±3 over ±1, ±3, and ±9. So let's see what we can get. I can get 1 over 1, or I could get -1 over 1. Now, what I'm not doing is doing 1 over 1, 1 over -1, -1 over 1, -1 over -1. As we mentioned on the last slide, there's going to be some duplication there. So I'm just making each possible choice up to a plus or minus, and then remembering that I'm going to have both the positive and the negative. Okay, so similarly, I can have 1 over 3 or -1 over 3. That would be by choosing this choice for p and this choice for q. So 1 over 1, 1 over 3, 1 over 9, 3 over 1, 3 over 3, 3 over 9. And I have plus or minuses on all of those. Okay. All right. Now if I simplify this down, there's actually some further redundancy. For example, 3 over 3 is just 1, and I already have a 1 in the list. -3 over 3 is -1, and I already have that. 3 over 9 is the same as 1 over 3, and that's already in the list. And -1 over 3 is also in the list. So there was still some redundancy even after accounting for the plus or minus business. That can happen. So we've got 1, -1, 1/3, -1/3, 1/9, -1/9, 3, -3. Any rational number that is a 0 of the polynomial must be in this list. They can't possibly all be. Okay, my polynomial was of degree 7 up at the top. You can see the highest power of x is 7, so this is a polynomial of degree 7, which means it can have at most 7 roots. I've got a list down here at the bottom of 8 numbers. There's no possible way they could all be roots. The rational roots theorem does not tell you these are all roots. It merely gives you a list of possible candidates, and it's exhaustive in terms of rational numbers. There is no rational root that won't be in this list. Okay, now what changes in the problem is we're supposed to use the zeros to factor the polynomial. So this is a polynomial, the coefficients are integers, so any rational root must be of the form plus or minus factors of the constant term, 15, over factors of the leading coefficient, which is 1. Having a leading coefficient of 1 is nice because the only factors of 1 are 1 and -1, which makes this quotienting a lot easier to deal with. So we end up with factors of 15 are 1, 3, 5, and 15. The only factors of 1 are 1, and I have to remember to have a plus or minus of all of these. So we have 1, -1, 3, -3, 5, -5, 15, -15. Okay, they can't all be roots because I've got 8 numbers here, and this is a degree 3 polynomial. But maybe some of them are, okay? So for example, is f of 1 a root? Well, I get 1 cubed minus 1 squared minus 17 times 1 minus 15. This is 1 minus 1 minus 17 minus 15. You know what this isn't? It's not 0. Okay, there's too much subtraction going on. It's just not going to be it. It's -32, but whatever. It's not 0. So this isn't a root. Okay. F of -1. What I'm hoping to do is find a 0. Okay, and we'll see why. This gives me -1 cubed minus -1 squared minus 17 times -1 minus 15, or -1 minus 1 plus 17 minus 15, which is 0. So -1 is a root of the function. Okay? Maybe some of the other numbers are, but as soon as I find a root of the function, I like to immediately say, okay, great. I'm going to use that information to my advantage by doing polynomial division. Okay? If -1 is a root, then x minus -1 is a factor of f of x. In other words, if I do polynomial long division with x plus 1, there's not going to be any remainder. It's going to actually exactly factor out. Now, I know many of you are probably used to doing synthetic division. It never really stuck with me. I always just end up doing polynomial long division, which works in situations where synthetic division doesn't, which is why I've never really made an effort to have synthetic division stick in my brain. So how many times does x plus 1 go into x cubed? It goes in x squared times, giving me an x cubed plus x squared. If I subtract this off, we have now -2x squared, not 22, sorry. How many times does x go into -2x squared? -2x times. Bring down -17x. This product now gives me a -2x squared minus 2x. If I subtract this, we end up with -15x minus 15, which goes in exactly once, -15x minus 15 for no remainder. So what this here tells me is, I'm essentially now going to go back to the beginning of the problem and start all over. But this polynomial long division has given me a lot of really great information. What it tells me is that this polynomial I started with can be exactly factored as x plus 1 times x squared minus 2x minus 1. Okay. So now I want to factor this more, but what I have left is a factor that I've already determined and something else which is now of degree 2. Anytime you see something of degree 2, don't forget you already know how to factor degree 2 polynomials. It's called the quadratic formula. Okay? Finding a degree 2 polynomial in a problem is a tremendous relief. Okay? The quadratic formula might be a little tedious, but it's something we've all practiced and have gotten very used to dealing with. So let's just ask, how does x squared minus 2x minus 1 factor? In other words, what are the x's for which this is equal to 0? Well, if I apply the quadratic formula, we get -b, which is going to be positive 2, plus or minus the square root of b squared minus 4ac over 2a. So 2 plus or minus the square root of, let's see, this is 4 plus 4 over 2. 2 plus or minus root 8 over 2, which simplifies down to 1 plus or minus root 2. Okay, so now we found some roots. This second term factors as x minus the first root, 1 plus root 2, and x minus the second root, 1 minus root 2. When we use the rational roots theorem, these two numbers were not in our list of possible roots. It doesn't mean they can't be roots, it just means they're not rational numbers. 1 plus root 2 and 1 minus root 2 cannot be expressed as one integer divided by another. So the rational roots theorem was not going to give them to us as possible roots. Remember, the rational roots theorem gives you a list of numbers. They are all rational, they're all a whole number over a whole number. If a rational number is a root, it's in that list. Not everything on the list is a root, and there might be roots that aren't in the list if they are not rational numbers like these. All right, again, this is a polynomial. The coefficients are all integers, so great. I'm going to apply the rational roots theorem. Any rational root, p over q, is of the form a factor of the constant term, which is 1, over a factor of the leading coefficient, which is 2. So this is a pretty short list, okay? It's either 1 over 1, -1 over 1, 1 over 2, or -1 over 2. They can't all be roots. Hopefully some of them are. So let's start checking. And you know what? I'm going to check the easy ones first. So let's try plugging in 1. I get 2 times 1 cubed minus 1 squared plus 2 times 1 minus 1, or 2 minus 1 plus 2 minus 1, which is not 0. Oh well. Let's try minus 1. 2 times -1 cubed minus -1 squared plus 2 times -1 minus 1, aka -2 minus 1 minus 2 minus 1, definitely not 0. Oh well. So we keep going. Let's try plugging in 1/2. I get 2 times 1/2 cubed minus 1/2 squared plus 2 times 1/2 minus 1. This is 2 times an eighth minus a quarter plus 1 minus 1, or 1/4 minus 1/4 plus 1 minus 1, which is 0. So 1/2 is a root. So I could check the last one, but I usually like to just go ahead and get to factoring as soon as we have found a root. Now, if a root is given by x equals 1/2, then a factor must be given by x minus 1/2. Once I set up polynomial long division with fractions involved, however, while it's doable, it can get really ugly. Okay? So here's a hint. If you find a fraction as a root, and you have this x minus a fraction as a possible factor, multiply by the denominator. So if I multiply this by 2, I end up with 2x minus 1. Try that as a factor. So let's go to polynomial long division. I want to factor 2x minus 1 out of 2x cubed minus x squared plus 2x minus 1. 2x goes into 2x cubed, exactly x squared times, giving me 2x cubed minus x squared, which subtracts off exactly evenly. So I just bring down my 2x minus 1, and there we have it. That goes in once with no remainder. So I can now come back to the beginning of the problem, having done this long division and verified that there is no remainder, so I have found a proper factor. So I come back up here and I say, okay, this can be factored as 2x minus 1 times x squared plus 1. X squared plus 1 is a degree 2 polynomial. So if I want to continue my factoring problem, I don't have to start all over. I can jump right to the quadratic formula because that's of degree 2. Now, if we try applying the quadratic formula to this remaining quadratic term x squared plus 1, I'd say, where is x squared plus 1, 0? If I apply the quadratic formula, we get x is equal to negative b, which is 0, plus or minus the square root of b squared minus 4 times a times c over 2a, or plus or minus the square root of negative 4 over 2, which is not a real number. I have a negative quantity under that square root sign. I have what's called a negative discriminant. So this has no roots, which means x squared plus 1 cannot be factored anymore. This is what's called an irreducible quadratic. It can't be factored anymore because it doesn't have any roots, so we're done. Okay, once you hit an irreducible quadratic term, that can't be factored. And the only thing other than that irreducible quadratic is that linear term of 2x minus 1, which we've already factored out.